Rayleigh's criteria for resolvability. Resolvability, the fact that the lens images are diffraction patterns, is important when we wish to distinguish two distant point objects whose angular separation is small. Rayleigh's criteria for resolvability is from UK. The angular separation of 2 point sources is such that the central maximum of the diffraction pattern of one source is centered on the first minimum of the diffraction pattern of the other. Look this way. We have 2 separate point sources. We want to separate it. Now this is angle theta 0. Okay. Now, so this one, the maximum is the first minimum of the second one. Or this one, the maximum is overlap with the first minimum of the second forces. Okay. Actually, this angle is the first minimum position. Okay. And we look at it, the pattern on the screen. The screen is local the focal plane. So the difference delta x equal to theta phi, right? Theta I phi. And we know this one, theta r from Rayleigh's criteria is the first minimum for the aperture diffraction. So theta r should be arc sine 1.22 lambda over d. When the theta is very small, so sine theta approximately equal to theta. So theta r equal to 1.22 lambda over d. Now let's look at the picture. This one, you cannot tell 1 or 2, basically, so this is the 1. And this picture, you see, oh, it might be starting at 2. And from this picture, you can choose, this is a 2 object, okay? Now, this is 2 to very close, a little bit separate, this is separate, okay? So this figure shows the visual appearance and corresponding intensity patterns for 2 distant points objects, say stars, with small angular separation.
This black screen has 5 pairs of slits through which light passes from behind. Each successive pair of slits is separated by half the distance of the pair above it. The upper pair of slits can easily be seen as separate, but pairs of slits lower down become progressively more difficult to resolve as separate slits. As the camera moves in, these closer pairs of slits are progressively resolved as separate slits.
Rayleigh's criteria for resolvability is only an approximation because resolvability depends on many factors such as the relative brightness of the sources and their surroundings, turbulence in the air between the sources and the observer, and the functioning of the observer's visual system. However, for the sake of calculations here, we shall take theta 0 equals 1.22 lambda over d as being a precise criteria. If the angular separation theta between the sources is greater than the theta r, we can resolve the sources. If it is less, we cannot. When we wish to use a lens to resolve objects of small angular separation. It is desirable to make the diffraction pattern as small as possible, theta small. Okay. Smaller theta, we need lambda smaller, d is larger. This can be done either by increasing the length diameter d or by using the light of a short wavelength. For this reason, ultraviolet light is often used with microscopes because it's shorter wavelengths. It permits finer detail to be examined than visual light. In an electron microscopy, such beams may have an effective wavelength that is 10 to the -5 of the wavelength of the visible light. They permit the detailed examination of tiny structures. Sample. Two distant points, we want to separate it. Okay? This is a screen is on the focal plane. So dx equal to f theta I. Okay. A circular converging lens with diameter d 32 millimeter and the focal length f 24 centimeter forms images of a distant point object in the focal plane of the lens. Light of wavelength lambda 550 nanometer is used. Question A. Considering the diffraction by the lens, what angular separation must two distant points objects have to satisfy Rayleigh's criterion? Now, this is the angle. This should be larger than this one, right? Theta Rayleigh. Now, we put the number in sign. Very simple. Lambda is 550 10 to the -9 meter. The d is 32 times 10 to the -3 meter. So we get answer. The theta, the angle between them must be larger than this one. Question B. What is the separation delta x of the centers of the image in the focal plane? Well, that's very simple. Okay, delta x equal to f theta. We put theta I, we put f, we get the answer. Okay, get the answer. It's 5.0 micrometer.